recording is started and we will start our class. And make sure you let everyone into the meeting as well. All right, let's start off with 1990 Amy number 4. So what is, our problem is going to be what is 1 over x squared minus 10x minus 29 plus 1 over x squared minus 10x minus 45 minus 2 over x squared minus 10x minus 69 equals 0. You want to find what are the values of x. So I'll give you a minute to think about how to do this problem. All right, I've given you a decent amount of time. So the first thing that you should notice is there's a lot of x squared minus 10x, right? So let's get rid of all that because seeing that over and over again, it's a pattern. We can use a substitution on it. So our substitution is going to be a equals x squared minus 10x minus 29. These Zoom notifications are out of hand. I'm going to mute them. And there you go. That should stop all notifications. All right. So like I said earlier, our substitution is a equals x squared minus 10x minus 29. And if we apply this substitution to all of our terms, we get 1 over a. Let's change the color. 1 over a plus 1 over a minus 16 because we have a 45 instead of a 29. And then plus, sorry, minus.
Is it okay if we use a color other than blue or any other dark color?
Oh, is this the blue too dark? Is this all right? Can you see this one?
I think it should be good. They said yeah.
All right, that's good. So this will be a minus, and then 69 minus 29 is equal to 40. And it's going to equal 0. Now, since we have a lot of these fractions, we can multiply everything now by a times a minus 16 times a minus 40. So this is going to become a minus 16, a minus 40, plus a times a minus 40 minus 2 times, remember there's a 2 there, 2 times a minus 16 is equal to 0. We can bring the 2 over, the minus 2 times a minus 16, we can bring it to the other side, so let's do that. And let me just erase all this to make it clear and bring this over here. And now we can expand everything out, right? So let's do that. Starting with the left term, a minus 16 times a minus 40, that's going to equal a squared minus 56a plus 640. Moving on to our second term, let me auto minimize, plus a squared minus 40a. And this monstrosity over here is equal to 2a squared minus 32a. Now, if you take a look at this, the a squared terms cancel out, right? So the 2a squared will drop out. And some of the a's will cancel, and you're going to be left with 64a is equal to 640. So a equals 10. Remember, we're not done yet. We found the value for a, but we want to find the value for x. So we're going to substitute back in to the original x. So 10 equals x squared minus 10x minus 29. And this will become x squared minus 10x minus 39 equals 0. You can factor that to get x minus 13 x plus 3 equals 0. Now, since it's an Amy problem, they're asking for the positive solution to x. And clearly the answer is going to be 13. This is an Amy number 4. So pretty easy for an Amy problem, but it is still an Amy problem, and it's a pretty good introduction into more difficult substitutions. Now, of course, the motif that we're looking for, like why did we substitute a equals x squared minus 10x minus 29? Because we kept seeing these x squared minus 10, x minus a constant. You keep seeing it over and over. And one of the key motif substitutions is to find these repeating patterns and replace them with something more manageable. And that's what our motif was for substituting for a. Next question, 1989 Amy. Find the square root of 31 times 30 times 29 times 28 plus 1. I'll give you a few minutes to think of that. Oh, not a few minutes, but like 1 minute. Don't type in chat yet. I'm gonna stop the sharing real quick so you don't see that. All right, I'm gonna share my screen again. Okay, take a look at Brian's message in chat. He explains why I put 0, 1, 3 instead of just 13. So let's look at the numbers we see here. We see a 31, 30, 29, 28. These numbers are right next to each other, right? And another thing you notice is that these are symmetric. Like, we're symmetric about this point, right? We have 30 on one side, 29 on one side, 31 on one side, 28 on the other side. So if you guys were there for the Monday class, we talked about the midpoint trick, where we substituted for, instead of x and x minus 2, we substituted for y equals x minus 1. We're going to do something very similar. We're going to say that our x is equal to, let me use the light color, x is equal to 29.5. And we can rewrite everything else, right? This is x plus 1.5 minus 5. And then x minus 0.5, x minus 1.5, and whoops, apparently need a longer radical. Plus 1. Now, why would I do that? It looks like we made things even harder, right? Well, now we can use difference of squares. And that's the whole motivation for the midpoint trick, right? We see these x plus 0.5, x minus 0.5. We can group those together using difference of squares. And we'll get x squared minus 0.25. And doing the same thing for the two remaining terms, we can get x squared minus 2.25 plus 1. We can do difference of squares again. We'll just say y equals x squared minus 1.25. And we'll get over here we get, let's change colors to make it more clear. Y plus 1, y minus 1 plus 1. Now if you expand the inside, you get y squared minus 1 plus 1, which is just y squared. We're square rooting y squared. So this just turns out to be y, because we know that we're looking for a positive answer. So we know that whatever this is, whatever this mess is, it's going to simplify to y. So what is y? We know x is 29.5. So 29.5 squared, it's just a tiny bit hard to calculate, but it's not too bad. You could think of it as 295 squared divided by 100. And if you know the trick for squaring with numbers that end in 5, you just do 29 times 30, and then add a 25 at the end. And we're dividing by 100, so 870.25. So y is equal to 870.25 minus 1.25. So the answer is y equals 869. And that is our answer. It's a good amount of computation, but this is Amy after all. Amy, you have 15 questions in 3 hours. So you can say, like, for the early problems, this is a decent early problem. You'll be at about 6 or 7 minutes per question. So much more than you're accustomed to for AMCs and math counts. And again, the overall idea behind this problem was look at a bunch of symmetric numbers, realize you can use the midpoint trick to get a bunch of difference of squares. After you do these kind of problems, you'll start to identify these patterns quickly. This one appeared on this year's test, AMC 12B, and it was a pretty hard question. I don't think I actually solved this in the time given. This is a problem number 22. And the question is, what is the maximum value of the quantity 2 to the t minus 3t times t all over 4t? So I'll give you a couple minutes to solve this, or at least get a way towards solving it. Sorry about that. Phone went off over here. Don't worry about it.
Naveen, I think you're muted.
Yeah, I got muted. I don't know what was happening there. So what I was saying earlier was that we're going to split our 4 to the t to 2 to the t times 2 to the t, because we have a 2 to the t over here. So we're thinking maybe we can do some kind of substitution that allows us to replace 2 to the t. So we're going to split our fraction up into 2 parts. We have on the left part of the fraction, whoops. On the left part of the fraction, we have 2 to the t minus 3t over 2t, 2 to the t. On the right side, we have t over 2 to the t. Now you see this, if we actually break this fraction up on the left-hand side, because we have a 2 to the t, you can break this up into 1 minus 3t over 2 to the t times t over 2 to the t. Now look at this. We have a t over 2 to the t in both fractions. And that's very complicated. That's a linear and exponential combined together, which is hard to manipulate. So we can substitute it out entirely. So let's say that t over 2 to the t is equal to a. So let's rewrite our product of fractions. Okay, 1 minus 3a times a. This is a lot nicer. And we're trying to find the maximum value of this, right? And the maximum value, this is a quadratic. The maximum value of a quadratic is going to be the average of the roots. And this is pretty easy to prove if you just took a random quadratic function. That's not very nice. If the roots are here and here, the maximum value is going to be in the middle of those two roots. So let's find those two roots. Let's set this to equal to 0. The first root is going to be a equals 1/3. The second root is a equals 0. So therefore, our max value occurs at a equals 1/6. So we just only found a though. We need to find the actual value, right? So let's plug that in. Let's see what happens when you plug 1/6 into this. Let's move over here. Let's create some more space. All right, we're back. Plugging 1/6 into this, we get 1 minus 3/6 times 1/6 is equal to 1/12. And that's our answer. That's the maximum value of that function. And we are done. All right, let's move on to the next question. We're back to radicals. And let's look at this problem. Evaluate 52 plus 6 square root 43 to the 3/2 minus 52 minus 6 square root 43 to the 3/2. So I'll give you about a minute to think about how you can approach this problem. This is from the 1990 Amy. All right, so give you some time. So we have this nasty 3/2 in the expression, right? So we can try to rewrite that. I think someone was PMing me about what that 3/2 means. It basically means the square root of the cube. So let's actually write it as a square root of the cube. So we'll rewrite this as, okay, that's a little too dark, right? 52 plus 6 square root 43. This cubed minus 52 minus 6 square root 43. This cubed. So if you look at this, the inside of those terms, this square root 52 plus 6 square root 43. If you're here at the Monday lesson, that looks pretty familiar. We have this, this kind of problem where we're able to decompose it into two different, well, denest into two different radicals. Let's see if we can do the same thing here. Whenever you see this kind of nested radicals with the square root a plus b root c, try to break it up into two separate radicals, and we're going to try that. So let's square this. We get, let's say that this equals square root a plus b, right? That this right here is the sum of two radicals. And let's call that square root a plus b. Square root a plus square root b, sorry. So let's square all this. So on the left-hand side, we get a plus b plus 2 root ab is equal to 52 plus 6 square root 43. We can actually do a little bit better. 43 is prime. One of these has to be 43 or more, right? So we can actually write our square root a plus square root b to say square root a plus b square root 43. Squaring this, whoops. That's not what I meant to write. I'm sorry about that. But let's say squaring this, you should get a plus b root 43 is equal to that. That's a little bit better. This squared. I'm having trouble writing right now. There we go. That's what I meant to write. So now that when we square the left-hand side, we should get a squared plus 43b squared plus 2ab root 43 is equal to 52 plus 6 square root 43. And in the process of undoing, I deleted a 3. All right, there we go. Hopefully that didn't leave anyone too confused there. So now let's look at our equation. Clearly, a squared plus 43b squared cannot be a radical. So that must match up. Let's circle this part. This part must match up to this. Similarly, the 2ab plus 40 square root 43 must match up to this. Oops. So now we have two equations. I'm going to erase this and move it up a little bit further to create some more space so you can see it. A squared plus 43b squared is equal to 52, and 2ab root 43 is equal to 6 root 43. So instinctively, we should be able to cancel out the root 43s, and we get that ab equals 3. And over here on the left-hand side, 43b squared is pretty clearly the limiting factor, right? Like if b is greater than 1, b squared is, or 43b squared is too big. So b can only be 0 or 1. And it can't be 0 because a squared is not, a squared equals 52 does not give an integer answer. So b must equal 1. And if b equals 1, and then a squared equals 9, so a is equal to plus or minus 3. And this should be plus or minus 1. Which makes sense, right? ab equals 3. And over on the left hand, you have a equals plus or minus 3. And b equals plus or minus 1. So let's look at this. If ab equals 3, then either a equals 3, well, let's write that in better notation. AB is equal to 3, 1, or negative 3, negative 1. And the latter, this one, the negative 3, negative 1, you can just get rid of because the square root has to be positive, right? So AB equals 3, 1. What does this mean? Well, it means when we go back to this equation, it means that 3 plus square root 43 squared is equal to 52 plus 6 root 43. Let's write that down. So now what do? We repeat this for 52 minus 6 root 43. It's a very, very similar process, right? And we get that the answer for this can be simplified to 3 minus square root 43. I'm not going to go over the entire process since it's pretty tedious, as you just saw, but the same logic applies. So now we can rewrite the original question. Instead of saying 3 halves, we can say, what is 3 plus 43 cubed minus square root 43 minus 3 cubed? So let's do that. Now, if you guys don't know your difference of cubes, you should definitely at least memorize this. So let's just evaluate this, right? And in case you guys aren't familiar, here is the difference of cubes. What in the world did he write? This is pretty easy to verify if you expand everything out, right? So let's do that with our original equation. In this case, let me move this up. Our A is going to equal square root 43, and our B is equal to 3. So our 6a squared b is going to equal 6 times 43 times 3 . I think the battery's starting to die. Yep. Plus 18, plus 50, 36. I cannot speak. That is not right. I cannot do math. 54, sorry. And this should equal 828. So you saw me make a pretty silly mistake there, saying that 2 times 27 is 36. That happens still. Silly mistakes still happen. But you gotta try to avoid those and try to catch them when you can. So the answer is 828. This is a much harder problem to solve than it initially appears, to be honest, because there's a lot of chances that you just make a silly mistake in your computation. Let's move on to a cautionary tale. Can you guys see this color of green? All right, that's nice. So you guys might have seen this in a couple of YouTube videos because this problem got decently famous. What if you have x to the x to the x to the x is equal to 2? Find the value of x. And in a different problem, what is x to the x to the x to the x equals 4? And what is the value of x there? Let's make it a little bit lighter. I think some people are having trouble seeing it. All right, should be more visible now. So, you know the pattern. When you see a common pattern in a problem, substitute for it. So let's just set this is equal to y, right? So now you have, and you also know that this entire thing is equal to y. Whoops, hold on. That's not what I meant to say. What I meant to say is that this is equal to 2. And this is also, because this is also equal to 2. So it seems that x squared equals 2. So x equals square root of 2. Pretty simple, right? However, let's move on to the second problem to see what's wrong with this and why you gotta be careful. Change this to 4. X to the 4th is equal to 4. X is equal to square root of 2. Something's not right here. And you might be asking, how do you know which one is which? Or is it neither at all? The answer is that x equals square root of 2 works for x to the x to the x is equal to 2. And it does not for x to the x to the x is equal to 4. Now, why this is the case is beyond the scope of this class. But it's to let you know that if you see these kind of problems where you're repeatedly exponentiating a number over and over again, you might not get any solution at all. So please be careful whenever you see these power towers, because they just don't lend themselves easily to substitution. and do you run into the risk of accounting for extraneous solutions. The actual solution involves a lot of calculus. Okay, so someone's asking, how did I get x squared? What basically happened was that I saw the entire expression is equal to 2. So I saw the expression inside is also equal to 2. So I just said x squared equals 2 from there. You can see with the curly braces. And someone is asking, what is the solution for x to the x to the x equals 4? I'm not sure if there is a solution, because that sequence just might not exist. Like, it might not converge correctly. Let's move on to logarithms. So if you guys are there for the Monday class, you guys are familiar with the logarithm properties. But if not, I do have this over here in case you needed it. So just take a minute to look at this and make sure you know these before we move on to the harder logarithm questions. Because we're going to start off with an Amy problem. All right, let's move on to our Amy problem. Before that, well, let's do this one. So log 2 of xyz minus 3 plus log 5x is equal to 5. And we have 2 more equations like it. So we're going to introduce systems of equations with logarithms through this problem. So take about 2 minutes and look at this. If you're curious, this is 2016 Amy 2 number 3.
Naveen,
Yeah?
can you be a little, I think people are asking, can you be a little more clear on what the problem's asking?
Oh, yeah, sorry. Don't know why that's there. So the question is to find the value of log 5x plus log 5y plus log 5z. Yeah, that should have been included there.
Great,
And
awesome.
let's smooth that here. So some people have come up with a solution. So let's start talking about it. So right off the bat, we notice our logs on the outside, right? Those are complicating matters because they're making us think in numbers that we just don't know. Like, what is log 2 of this entire thing? Well, we can get rid of the logarithms at least the outside ones, by exponentiating everything. For example, this part right here is equal to 2 to the 5, which is 32. So let's write that down. It's equal to 32, and then we'll just add the 3, because there's a 3 inside all of this, and we'll do the same for the rest of them. For like our next example, this part is equal to 3 to the 4, which is 81. So let's write that down as well. Similarly, this part over here is equal to 4 to the 4, which is 256. Again, remember your powers of 2 until around 2 to the power of 15. All right, so we have 3 equations, and let's look at what the problem is asking for. Our problem is asking for log 5 plus x plus log 5y plus log 5z, the absolute values of those. So clearly, if we add everything up, let's look over here. We have this, which is exactly what we want, right? You know, without the absolute values, of course. So let's add everything up. Use a different color for this one too. 3xyz plus log 5x plus log 5y plus log 5z. And when you add all of these up, you're going to get 378. Gonna move that to the left a bit. So now what do we do? Well, we can combine those log 5s all together. They all have the same base, so we can group them together. 3xyz, 10%, okay. Is equal to 378. Now we have xyz. I am going to switch out and charge this. So let me know if the audio quality decides to be really bad. All right, how's the audio? Is it terrible or is it manageable? It's the same? Okay, there we go. That's great. So now we have xyz. We have a common term xyz, right? So now what do we do? Well, it's Amy, and we're going to use a little bit of guesswork, actually. We have an xyz in both terms, and we know that the answer becomes an integer, 378. So if log base 5 of xyz is an integer, then xyz is probably a power of 5. So let's try some powers of 5 out and see what happens. xyz equals 5. Well, that's too small. You shouldn't really have to think about that too long. Let's try 25. If you're wondering if there is a better way, then this is the official solution as listed in AOPS. So I really don't know if there's a better way to solve that. This one comes out to 77, which is still too low. However, the next time you try this, let's try 125, which is 5 cubed. We get 3 times 125 plus 3 is equal to 378. So xyz is equal to 375. And yes, this is kind of a cheese way of doing this, but it's valid. This is a legitimate way to do it. So xyz equals 125, right? Let's write that down, different color. And I have the floating bug of death with penbook, so I'm going to exit out. Penbook tends to glitch out when it does that for some reason. xyz is equal to 125. Now what? Well, we can substitute this x125 value into each of these equations. Yes. All right, let's do that. 125, gonna go back to white for a bit. 125 plus log 5x is equal to 35. 125 plus log 5y is equal to 84. 125 plus log 5y, log 5z is equal to 259. And from here, you get that log 5x is equal to negative 90. Take the absolute value of 90. Plus log 5y is going to equal negative 41. Log 5z is going to equal 134. You sum this all up and you get 90 plus 41 plus 134, and this is going to equal 265. And there's your answer. Now for Amy, your answers are going to be between 000 to 999. So there's a 3-digit answer each time. It's pretty good. Let's move on to H&MT problems. H&MT is the Harvard MIT Math Tournament. If you're not familiar with that, it's a subject-based test. There's tests for algebra, geometry, combinatorics, and number theory. There's 2 tournaments, the November and February. November is much easier than February. February is very, very hard. Like I went there and it was not good. I did pretty bad. But Andrew Klein, on the other hand, managed to place first place in combinatorics, and Luke demolished everyone. So yeah, let's look at this problem. So A is equal to 1/6 of that entire nasty expression. And you want to compute, this is not writing, 2 to the A. So after you find A, you want to find 2 to the power of it. I'll give you about a minute to do this because I want to get through the rest of the handout. All right, let's move on. We're running short on time, so we're going to move quickly with this one. So H&MT, like I said, pretty hard. So let's look at our expression. We have log 2 of 3, log 2 of 6, log 2 of 12, log 2 of 24. Each time you're multiplying the number inside by 2, right? But look at the base. This is log 2. And you might notice something. Log 2 of 6 is equal to 1 plus log 2 of 3. This is because log 2 of 6 is equal to log 2, 2 plus log 2, 3. And log 2, 2 is just 1. Similarly, log 2 of 12 is 2 plus log 2 of 3. Log 2 of 24 is 3 plus log 2 of 3. So now we can rewrite our expression, and this is going to get quite long, so prepare yourselves. It's not going to be as bad as it looks once we substitute correctly, though. Color time, 1/6. Let's see if this fits. Log 2, 3 cubed minus 1 plus log 2, 3 cubed minus 2 plus log 2, 3 cubed plus 3 plus log 2, 3. Oop, should be a plus. So the first thing you should notice, we have a lot of log 2s, right? Log 2, 3s. And remember, substitution, you try to find patterns and make those patterns look simpler to you, right? So let's say a is equal to log 2, 3. So now we can replace a lot of things, right? 1/6, and look how much this simplifies by. A cubed minus a plus 1 cubed minus, oops, a plus 2 cubed plus a plus 3 cubed. You can see the blue, right? All right, there you go. Some people are saying it's a bit hard. Okay, I'm gonna change it to light blue. There you go. And end parentheses. There you go, that should be much more visible. And I'll change the log 2, 3 substitution as well. So now we can do some algebra. Let's make this a bit simpler though for us, right? We have a lot of this. We have a plus 1 cubed minus a cubed. This is going to equal 3a squared minus 3a plus 1. It's a little nice trick we can use for this problem. So let's do that. 1/6, and we have our a plus 1 cubed minus a cubed. We're going to take the negative of that because we're doing a cubed minus a plus 1 cubed. So negative 3a squared minus 3a plus 1. Then over here, we have another form of a plus 1 cubed minus a cubed. It's just that we need to say, let's call it b. B is equal to a plus 2 plus 3b squared minus 3b plus 1. We can substitute our b back, and we'll get, let's minimize this again, 1/6.
Naveen?
Yeah?
Someone noticed that I think, so for a plus 1 cubed minus a cubed, you accidentally wrote minus 3a.
Whoops, yeah, you're right. There you go. That should be fixed now, I believe.
Yeah, just like for the b as well.
Oh yeah, you're right. All right, fixed. Thank you for catching that. So now let's plug our everything back in. 3a plus 2 cubed, a plus 2 squared, plus 3a plus 2 plus 1 minus 3a squared minus 3a minus 1. Bit messy, but it's H&MT. Pretty hard. this becomes, after you expand, the a squared terms drop out, and all you're left with is, I believe it's 12a plus, let's see, I believe that is 18. Yeah, this is what you're left with. And this will become 2a plus 3. So this entire mess simplified down to 2a plus 3. And now we want to find 2 to the power of a, right? How do you do that? I'm going to note some space down here to make sure you can see this happen. 2 to the 2a plus 3 is equal to, remember what a is? A is log 2 of 3. 2 to the 2 log 2, 3 plus 3. I'm going to erase this and create some more space because this might be a little bit too cramped. There you go. All right. And now this is just because a equals log 2 of 3. That was our initial substitution. You can break this up and say a is equal to 2 log 2, 3 times 2 cubed. Now what's 2 log 2, 3? Well, 2 log 2, 3 is equal to log 2 of 3 squared, which is log 2 of 9. So now what you're left with is 2 log 2 of 9 times 8. Now, this right here, 2 to the power of log 2 of 9, this is going to cancel out. You're just left with 9 times 8, which is 72. That's your answer. All right, now we're going to move quite fast. We're going to go into floors real quick. So floor equations, this one, so a trick with floors is we want to break them up into their floor component and their fractional component. So let's do that. Let's say that x is equal to n plus r, and let's plug that back in. So n is equal to floor of x, r is equal to the fractional part of x. So let's rewrite our equation. N plus r squared minus 8n plus 7 equals 0. Now when we expand this, we get n squared plus 2nr plus r squared minus 8n plus 7 equals 0. We can factor out an n, and we'll get n squared plus n 2r minus 8 plus r squared plus 7 is equal to 0. Now the reason we did that is so we have a quadratic formula for n. This looks like our ax squared plus bx plus c form, right? Let's make this a little bit cleaner. Remember how quadratic formula, we proved it by completing the square? We're going to do the same thing here. Now completing the square, let's say we had x squared plus bx plus c. This is going to become x squared, x plus b over 2 squared plus some constant k, right? So our b is 2r minus 8. So b over 2 is going to become r minus 4. So that's going to become n plus, sorry, r minus 4. Did I say that I might have said r over 4, I meant r minus 4. And how much do we need to add to both sides? Well, r minus 4 squared is equal to r squared minus 8r plus 16. And we had an r squared plus 7 earlier. So we need to add 9 minus 8r to both sides. So this is going to become 9 minus 8r. Let me move this. So now it's kind of clear that we can square root these, and we get n plus r minus 4 is equal to plus or minus 9 minus 8r. So n, our integer value, is going to equal 4 minus r plus or minus square root 9 minus 8r. So this entire process was to isolate n. That is the reason, that's the motivation behind all of this. Why we do that? Because we know n is an integer, which means that negative r plus or minus square root 9 minus 8r has to be an integer. What else do we know about r? Well, we know that r is a fractional part of a number, right? And what else do we know about that? We also know that 9 minus 8r has to fall in the range between 1 and 3. Because this cannot be greater than 9. This cannot be greater than 9. And since r is 1 at maximum, 9 minus 8r is equal to 1. So we know that this is going to fall between 1 and 3. And I'm going to, this is less than because r cannot equal 1 exactly. So now we got a couple of cases to check, right? So negative r can be, let's write this down as well. Negative r can be between 1 and negative 1 and 0. So now what can this negative r plus or minus square root 9 minus 8r be? Got a couple of cases since we know it has to be an integer. So I'm going to create a new slide for that. Won't let me create a new one. Oh, no worries. I'll just move everything again. I don't know why it's not letting me create a new slide, but okay. I'll just delete this one here. So let's write down what we're looking for. We want negative r plus or minus square root 9 minus 8r to be an integer. Now, if you look at this, there's only a couple cases that can happen. Either this equals 1, 2, 3, negative 3, or negative 2. You can verify this by looking at these conditions. So now what do? We're going to solve the first case and set it equal to 1. So let's say that negative r plus minus square root 9 minus 8r is equal to 1. Let's move our r to the other side so we can square everything to get rid of our plus and minus and a radical. So plus or minus square root 9 minus 8r is equal to 1 plus r. Squaring this, we get 9 minus 8r is equal to r squared plus 2r plus 1. And when we simplify this, we get that, I mean, we solve a quadratic formula as well. We get r is equal to minus 5 plus or minus square root 33. Remember that 0 is less than r is less than 1. So we can get rid of the negative solution. That is an extraneous solution. So therefore, as r is equal to negative 5 plus the square root of 33. And in this case, n is going to equal 5. So x is equal to square root 33. This is the case for the expression is equal to 1. There's still 4 other cases that we're going to check. And since we do have a time constraint, we're not going to go over those other cases, but they're going to be in the handout that we release. So we won't provide the solutions. They're meant to be solved by you. But in case you wanted to check your work at the end, you should get x is equal to 1, square root 33, square root 41, and 7. Please work those problems out because they will help you actually understand what you learned today. We're going to go over maybe 1 or 2 more questions. So let's get rid of that. The video should be up by tomorrow. So our next question is a systems of equations question. And it's going to ask, as soon as I can erase all this. You have 2x1 plus x2 plus x3 plus x4 plus x5 is equal to 6. x1 plus 2x2 plus x3 plus x4 plus x5 is equal to 12. x1 plus x2 plus 2x3 plus x4 plus x5 is equal to 24. Just going to write the rest. So I'm just going to go over the solution since we're running short on time. You notice a lot of symmetry, right? You have 2, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 1, 2. Those are the coefficients of each of your equations. So if you add all those up, everything's going to become the same, right? If you add all these up, you're going to get 6 x subscript 1, x2, x3, x4, x5 is equal to 186. So x1 plus x2 plus x3 plus x4 plus x5 is equal to 31. And you're looking for, the question asks, what is 3x4 plus 2x5? How do you find x4 and x5? Well, if you look at this equation right here, and look at the equation where you have 2x4, they're very much identical. All that's left over is an x4. So you can subtract those two equations. And when you do that, you're going to be left with x4 is equal to 17. Similarly, you can subtract this equation from this equation to find x5. And you're going to be left with x is equal to 65. So 3x4 plus 2x5, pretty straightforward. This is 51 plus 130. which is going to equal 181. Last question of the day. There's going to be more questions in the handout, but due to our time constraints, that's not entirely possible to go over all of it. It's definitely a more involved week than most. And I can erase all this. So calculate 1 plus 3 plus 3 squared plus 3 cubed plus 3 fourth dot 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 plus 3 to the 9th. Now, like, your first instinct might be to sum all of these up, right? So turns out summing them up is not the most efficient way to do this. It's very, very silly prone, and I can almost guarantee you that it's going to take longer than the trick that we're going to do. Now, if you guys know what polynomials are, this is a polynomial problem in disguise. So what we can do is set x equals to 3, because there's so many 3's, right? We can assign a variable to all of it. Now we have 1 plus x squared plus x cubed dot 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 plus x to the 9th. Now why on earth would we do this? Well, we can do this to manipulate the equation a bit. Well, the expression. There's a lot of like terms. So we're thinking maybe we can cancel some terms out to leave us with a super nice answer. And since we're multiplying each term by x, let's multiply the entire sequence by x. So when we do that, we get x plus x squared plus x cubed plus x to the 4th plus dot 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 plus x to the 10. There's a lot of like terms. If we subtract these two sequences, we're going to get a lot of canceling. So let's subtract these two terms, these two expressions. These two cancel, these two cancel, these two cancel, everything cancels. All that you're left with is x to the 10 minus 1. So how did we arrive at x to the 10 minus 1? If we take our original sequence, we multiplied it by x and then subtracted the original sequence. That's the same as multiplying by x minus 1. So that allows our first identity, which is saying that this x to the 10 minus 1 is equal to 1 plus x squared plus x to the 9th times x minus 1. We can generalize this. We say that x to the n plus 1 over n minus 1, well, sorry, x minus 1, not n, is equal to 1 plus x squared plus x to the n. Let's apply this to our original problem. We can plug in back 3. And now what we know is that we're looking for 3 to the 10. This should have an x minus 1 over 3 minus 1 is our original expression. 3 to the 10 is a little bit hard to compute, but if you know 3 to the 5, which you should, 3 to the 5 is 243. You can calculate 243 squared without too much issue. At least you can do it on paper, and you'll get 59049. And this over 2, well, this minus 1 over 2 will give us an answer of 29524. And that is how to solve these infinite geometric series. There's going to be a lot of problems on the handout that we haven't gone over. And the solutions will be there as well. And as always, we'll have homework problems. So be sure to check out the handout. It should come by either tonight or tomorrow afternoon. Since we're running over on time, we're going to end the meeting here. Thank you all for coming. I think we had around 250 participants at the peak time. So that's great. See you all. If you guys want to ask any questions, I'll be here for a slight bit. And